My name is Matthew Lang. I'm Director of Professional Services at Continuent. And we actually have a special guest as well, Matthew Churcher, the Performance Engineer at New Voice Media. Thanks a lot for joining us. So just a little bit about me. I've been doing databases for a while, and I started off working with a database called Progress, which no one has ever really heard of. And basically, we were working in our company, and like everyone else, we wanted a website. Developers wanted to be able to use advanced features that MySQL had, but Progress didn't support it. So we did what anyone else would do. We wrote some batch scripts from Progress and pushed everything to MySQL. So we did that once a day, and after a while, that really wasn't enough. So we did it 2 times a day. And then we started doing it hourly. And then we started thinking, well, maybe like every 15 minutes we should update this table. And it actually really became a mess. Our data was stale. This batch loading thing would die sometimes in the middle of it. We'd have to go and kind of debug it and try to figure out what's up. And we really weren't accomplishing our goal. So I wrote a real-time replication little engine from MySQL to Progress. And that's how I became interested in MySQL. That's how I became interested in database replication. I became a DBA sysadmin. And from there, I became a site reliability engineer for a healthcare company. And this healthcare company services doctors. And basically, the mandate was the site cannot go down, because if the site goes down, doctors can't treat patients. And that's not a good thing. So in that time, we used Continuent products for high availability and disaster recovery. And I really love the product so much that here I am now with Continuent. So a little bit more information about Continuent. We're back. We were purchased by VMware about 2 years ago, or maybe 2.5 years ago. And after about 1.5 years, VMware discontinued our products. At that point, they really didn't have a need for us. But we're spun off, and we're back. We're completely independent. And the original Continuent team, many of them have come back to Continuent. So it's all the original people that you're dealing with Continuent. We also have our Tungsten Replicator, which is open source, and probably a lot of you have heard of it or are even using it.
Come to my talk tomorrow on Thursday.
Yes, come to MC's talk tomorrow on Thursday to learn more about that. So we do high availability for MySQL. We do disaster recovery, business continuity. We have high performance replication. So not only do we replicate MySQL, we replicate from MySQL, from Oracle, to MySQL, Oracle, and various data warehouses, MongoDB, Hadoop, Vertica, Amazon Redshift. So we support a lot of companies that are dealing with real-time analytics as well. So on to the actual presentation. So this is the dream, which I'm sure everyone dreams about constantly, is to basically have your databases geographically spread out over the world servicing your customers. And they're always in sync, and they're always up and available. And any updates that you have to one database is immediately propagated to all the other databases around the world. Okay, so one of the first kind of technologies to do this was using synchronous replication. And this is how some other products work. For instance, Galera, right? So there's some group communication going on when you write to the databases. And this group communication orders the transactions and then writes all these transactions to all the appropriate other database. So this is kind of a classic distributed scenario. Right? So the problem that we sometimes run into with this kind of technology is, well, what happens if you get 2 writes at the same time, 2 inserts with the same ID number, right? One of these writes is definitely going to fail. And when that happens, you have to do some sort of remediation, right? And your replication is stopped, your one database is offline, and you actually have to go in, manually remediate it, and really reprovisioning one of these databases could take hours, it could even take days, but it's a really huge disruption to your cluster. Okay. So what other issues are there with synchronous replication? So over long distances, this really doesn't work too well. Because when you write to your local database, your application can't continue until it gets a message from all the other databases that this commit is going to succeed on those databases. So if you can imagine geographically distributed databases, US, Europe, a write to US, right, has to be propagated to Europe and acknowledged that that write has actually been successful before your application to continue. So you're introducing a lot of latency in your application. Large transactions, right, long-running transactions can really introduce some high latency. So really for this reason, synchronous replication does not lend itself to replicating over long distances. Oops. Well, okay. So we at Continuent, and basically 8 years ago, we wanted to take a different look at things. So can we do this? Can we get high availability, disaster recovery? Can we do multi-site, multi-master? And we can. So we've been doing this for about 8 years now. It's a very mature product. We can do high availability, clustering, and we can replicate over large distances without a change to your application, without any additional latency to your application, and without any recoding of the application or even your databases at all. And it's a single solution with a single management interface. So this is kind of to talk about multi-site, multi-master. I first want to talk about high availability in a local cluster. If you think about it, if you have multi-site, multi-master, that's great, but if you don't have high availability locally in your data center, if that data center goes down, then you no longer have multi-site, multi-master because you only have half the picture there. So I want to talk about this high availability. So we take MySQL, right, and we don't actually change anything in MySQL. We don't change anything in your app. We just install a couple extra pieces on the database servers, and then we have this other kind of proxy, intelligent proxy, that we call the connector, right? So what this kind of shows here is a master DB1, 2 slaves, right? And the application is actually connecting to the cluster via this connector, right? And so what does this connector do? Well, this connector actually presents this whole cluster, all these databases, as a single data source. So your application is connecting to the connector. It's not aware that there's actually, in this case, 3 databases in the background here. The connector takes, excuse me, the connector takes care of all the connectivity to the databases. And the connector is actually in contact with each of these nodes and knows who's the master and who's the slave. So in here, we have a single solid line, or a couple solid lines pointing to DB1. Those indicate writes, right? So we're always going to write to the master. Optionally, we can configure the connector to read from the slaves if we want to. And we have a whole bunch of rules, and I'll get into some of those, about reading from the slaves. So that's optional. By default, we read and write to the master, right? But we can do some sort of load balancing. We can spread the load by reading from the slaves if we want to. Okay, so a little bit about this connector. So this connector actually speaks the MySQL wire protocol. Typically, most of our customers actually install the connector on the application servers themselves. And the application servers point to the connector. So the actual connector's connection string from your application server is to the connector. The connector is aware of each state of each database server there. So it knows who the master is, and it knows who the slaves are. And this allows us to do transparent failover, right? So what does that mean? Well, if there's actually a failover, we can actually promote a slave to master, and I'll show you that as well. But what we can also do is we can decide where we're actually going to send reads. So like I said, by default, we read from the master and slave. But we have another feature called SmartScale, which can actually inspect the SQL, right? If it's an update, insert an update, delete, goes to the master. But if it's a select statement, we can possibly read from the slaves, right? What we also do, what we also keep track of is the latency on each slave. So we know for a particular session, a particular transaction, right? It's committed on the master. Has it made it to the slave or not? Has it been committed to the slave, right? So in this case, we've just written some data to the master, and it looks like we want to very quickly, within a millisecond, read the same data. So that first slave doesn't even have the data, so we don't want to read from that slave. The slave at the bottom has actually received the transaction, but it hasn't been committed yet. So we're not going to read from that slave. So in this case, we're going to read from the master to make sure that we have consistency. However, if maybe it's a half a second later, what's happening here is we want to do a read, and we see on that first slave, it's received the transaction, but again, it hasn't committed it, so we're not going to read from that slave. But this other slave actually has received and applied, committed the transaction. So that's definitely a candidate that we can read from. So, and this is all configurable, and it's optional if this is something you would want to use. But you could do this, and actually you could kind of scale this out. So instead of 3 or a master and 2 slaves, you could have a master and 4 slaves, and even spread the load out even more. So it's a pretty powerful feature, and it allows us to get a lot better performance and not load down the master so much. So these are some of our methods for determining load balancing, right? So the inspection of the SQL that I just talked about is called SmartScale. Right? We actually look at the SQL and make a determination, is this a read or a write? We can do something called direct reads. We can say, this user, we want to prefer a slave all the time. And it'll attempt to go to a slave. We can do host-based. So we can define two host names in our connection string. Right? So when we specify this host name, it's going to be a read. Specify an alternate host name, it's going to be a write. We can do port-based. So our connector can listen on 2 ports. Right? One port would be your read port, one port would be your write port. And we actually see customers do this because they've already, even before they've actually spoken to us, they've actually designed in their application different connection strings based on read or write. So by specifying port-based, they can use their write connection string just by specifying a different port, or their read connection string. And then finally, we can inspect the SQL and look for a comment in the actual SQL string itself. And when you do that, with the comment, you can actually specify, we prefer a slave or we prefer a master. So, and in all these cases, we can actually look at the applied latency on the slave. And if it's above a certain threshold, then we know, okay, maybe that slave is stale, we don't want to read from it. So we override it. And you can specify how much latency, a couple seconds or 10 seconds, whatever. Okay, so here's now kind of the full picture of our clustering solution, right? There are basically 3 components. So the first component is the connector, which I just talked about. So that's the intelligent proxy, normally installed on the app servers, but it doesn't have to be. You can actually have connectors running on the database servers if you want, right? Then we have our replicator piece, which I'll definitely get into. But our replicator manages all the replication to and from masters and slaves. A replicator can have different roles. So a replicator can be a master, right? It can be extracting from the master, or it could be applying to a slave. And in the event of a failover, those roles can actually change. And then there's the manager. And the manager kind of takes all this together. The manager directs the replicator what role the replicator should be. And it keeps in touch with the connector to tell the connector if there's any change as well in the database, in the cluster, right? So if a master goes away and a slave is promoted to master, the manager tells the connector about the new master. So what happens in the event of a failure? So here's a simplified view of a 3-node cluster. So the connector is connecting to the master for all writes and optionally all reads. Everything's being replicated to the slave. And the manager is actually keeping track of everything that's going on in the cluster. Who's master, who's slave, and updating the connector. The manager is also keeping track of statistics. So applied latency on the slaves. So if this master fails, the first thing we do is the manager detects this and then instructs the connector to hold connections to the cluster, right? So, and the reason why we're going to hold connections is because we need to promote a slave to master, right? So we promote the slave to master, but the applications are still connected through the connector, right? So what this means is the connector is kind of holding the connections for a few seconds, but the application is still connected to it. So you might have a small pause in your application, but your application actually never gets disconnected from the database. So a lot of applications respond very poorly when there's a disconnect from the database, right? And so the connector keeps the connection from the connector back to the app server open. So there's no disconnect. So finally, we promote one of our slaves. We pick the most up-to-date slave and promote it to master. And at this point, as an administrator, we can look at this node and decide, okay, is a server toast? Is the database any good or not? Maybe it's just a simple network blip or something like that. So if it needs to be reprovisioned, we have a command line tool to just basically reprovision that slave. So it'll restore the database and bring it back into the cluster. Optionally, if that node is actually still healthy and we can get it back online, we can actually bring it back into the cluster as a slave and let it get caught up. So all of this is transparent to the application. The application doesn't know anything about the back end that's going on here. But this is all automated.
So the slave to master promotion is automatic, and that just happens?
Yes.
There's no administrator intervention?
Right. So this all happens in the background, and it's completely automatic. And there are a whole bunch of rules actually that we actually look at to decide, is a master or even a slave if it's gone down. So can we ping it? Basic network connectivity. Can we log into MySQL? Is MySQL actually even running? But yeah, this all kind of happens. This all definitely happens in the background. And if you don't have good monitoring in place, then you actually may not know that it has happened. So, and we actually provide monitoring scripts for all this stuff. If there's a change in the cluster state, latency, we provide a bunch of scripts that work with Nagios, Zabbix, or even just command line shell. So we could also do this manually, right? So we can change roles in the cluster manually. And why would we want to do that? So we could actually do maintenance of our MySQL database or servers without taking our application down. So, and how we do that is kind of a rolling maintenance procedure. So here the example is resizing the MySQL log, the MySQL log file. It could be a patch, it could be a Linux upgrade, even a MySQL upgrade. But the basic idea is we upgrade the slave, right? We take it out of the cluster, we upgrade it, and then we put it back into the cluster when we're done with our maintenance. So master's still online, application is still happy. Then we do the exact same thing for the next slave, right? Do the same upgrade, bring it back into the cluster, right? When we're happy that all of our slaves have whatever change that we need to make and our maintenance is done on the slaves, we can actually execute a command called switch. And this just basically finds the most up-to-date slave, promotes it to master, and takes the current master and makes it a slave, right? So now the old master is a slave, and it's the one that needs to be upgraded. So we run our upgrade on the previous master, which is now a slave, and we're all done. So again, it's all transparent to the application because it's all done here at the cluster level, and the connector knows who's the master. And if there's a change in the state, the connector holds the connections until we can promote a new master. So this is, another way we get high availability, because with maintenance, maintenance could be hours, or it could be minutes, hours, who knows. But this way we don't have to take our applications down just for simple maintenance or for a hardware upgrade or OS upgrade. Okay, so now this button is okay. All right, so now let's get into the replicator, because this is kind of the glue that's going to hold everything together. So what is the replicator? So our replicator is included in our clustering product, but there's an open source version of our replicator as well, so feel free to download it. I have the link. But it's really a high-performance replication for MySQL and Oracle, and it can replicate to various data warehouses. So we can replicate, say, from MySQL to Hadoop. We can replicate, say, from 10 MySQL servers all into Hadoop, which we call fan-in replication. Vertica, we replicate to MongoDB, Amazon Redshift. And this is our own replicator, right? And it's also the core kind of feature for our multi-site, multi-master between MySQL clusters. So we're going to see that the replicator is kind of like the glue that's going to hold our geographic disjoint clusters together. There's an open source version, like I mentioned. We've been doing global transaction IDs with the replicator for about 8 years. So for us, global transaction IDs is nothing new. We have the option of doing parallel apply. So I'll show you that too, but basically we can apply transactions to the target in parallel. That's an optional feature, and it depends on how your database is set up and how your schemas are set up, but we do offer that. And instead of just replicate from source to target, we can do all kinds of topologies. What we call fan-in replication, so many sources to one target, fan out, one source to many targets, and filtering certain schemas or tables in the process, star replication, right? And we also have advanced filtering, so we can replicate certain tables, not replicate certain tables, do a time delay, so replicate after so many minutes, and there's really a bunch of filtering that we have. Okay, so our replicator is asynchronous, and the reason why is it decouples the transaction from the replication process. So why is that important? Well, when we actually commit a transaction to the master, we want our application to be able to return and serve the customers. With synchronous, what happens is you write to the master, and you have to wait till that transaction makes it to all the slaves, right? So there's definitely performance overhead for that. So we've chosen asynchronous, and the way our replicator works is we actually read from the MySQL bin logs. We read from the MySQL bin logs, and then actually repackage along with some extra metadata into our own format that we call THL, transaction history log. So the reason why we do that is because the replicator isn't just a MySQL replicator. We replicate to other targets, and this THL gives us the ability to not only replicate to MySQL, but we can replicate to all these other targets. Okay. So once we have it in the THL, the slave replicator retrieves that THL. All right? It brings it locally to the slave database and actually applies everything to the MySQL database using a regular JDBC connection. So this is all asynchronous. So when you write to the master, everything else happens in the background. Okay. And this is just a little bit more about our replicator, kind of the architecture. So we have actually several stages of the replicator. And so basically, we have the extract stage, right, which we extract from the master. And then from there, we can actually apply our filters at that stage. So we extract, and then maybe we can apply some filters, and then we can write it to the THL, right? Or at the slave, we can actually apply filters there. So that's kind of what this pipeline is. So extract, apply to THL on the master. THL gets shipped to the slave, and then we can extract from the THL. We can apply filters again at that point if necessary, and then we can and then we apply to the slave. So then this actually shows parallel replication if we choose to do that. So, for instance, if you have separate schemas that are completely independent, then parallel replication could be a candidate for you because we can apply in parallel those transactions to all these different schemas in parallel. Okay, so putting this all together. So this is what our multi-site, multi-master complete topology would look like for 2 sites. We support more than 2 sites. It could be 3, 4, 5, 6. How many feasibly you would want. But this is the same picture as before. So we have our cluster. This would be our cluster in San Jose. We have a cluster in New York. And each cluster is being served by its app servers locally to it. We have the connector connecting to the local clusters. And then in between, we have this asynchronous replication happening between the 2 clusters. So we can have 3, 4, and what happens here is a write to here will get propagated over here, but the application is not going to wait for that propagation. So you still have good performance on your application, but in the background, asynchronously, you have replication going in both directions. So and I just want to point out that there's no performance penalty by having multi-site, multi-master. Okay. And the reason why I went through the whole clustering kind of product is that these multi-site replicators can actually be configured to read not from a particular source on the remote cluster, but from the actual cluster itself. So let's say from San Jose, I want to read from New York. I don't have to specify who's the master, who's the slave, because the replicator already knows about that. Okay? And I can also specify that I want to prefer reading from slaves when I do my cross-site replication. And I would maybe want to do that so I don't put a whole, more load on my master. So we have a bunch of different sites, and geographically distributed. Maybe we want to pull those transactions from the slave so we don't put a whole lot of load on the master. Or maybe we prefer a master because we need the most up-to-date information. But typically it's by the slave. So we also support SSL for all of our replication pieces. And actually all of our clustering pieces too can be SSL. So we encrypt everything in flight if you choose. So again, this is where the high availability piece comes in. So I have a site over here reading from that cluster, right? And let's suppose it was reading from this slave that actually failed. the replicator automatically configures itself to read from the other slave or the master if necessary. So all this is also transparent. So what this means is a failure in one of the clusters is not going to affect all the other clusters because we can still read the data from another node within the cluster. And this is also where the global transaction ID really comes in handy because we know that where we've left off, if this goes down, we know where we've left off, we can ask the slave to start from that same location. So, what are all the requirements to do this? So we need SQL or MySQL. You need your application, but you don't have to change your application. All we really need is, obviously we need binary logging, right? That's kind of a requirement for replication. We need primary keys on tables. And optionally, we do these two things as well, auto increment offset and auto increment increment. Two parameters in MySQL, right? So what we do is, or what we can do is basically an update or an insert in San Jose. The primary key values are going to be 1. There's a typo there. Sorry about that. That should be 135. Okay. So basically odd numbers in San Jose, right? Even numbers in New York. And then when they replicate, there's no conflict. You don't have to do it like that. So some customers generate their own globally unique keys. So like a UUID or something like that. That's fine too. But configuring like this is a real easy and quick way to do multi-site, multi-master. If you have 3 or 4, whatever, you just change this auto increment to the number of clusters. So again, just putting it all together, 2 independent clusters, cross-site replication, asynchronous between them, and each cross-site replicator is aware of the status of the cluster and knows who's the master and who are the slaves, and who's online and if there's a node that's not online, we don't try to read from it. Okay. And I'd like to mention one other kind of topology. This is not multi-site, multi-master, but this is what we called HADR. So it's very similar. We have 2 regions, 2 clusters, and again, they're joined by a cross-site replicator, right? But we have a single master in this whole thing, right? This master right now is in San Jose, and we read and write to San Jose locally, but also we can have application servers in New York, but they're always going to write to this master in San Jose. They can read from they can read locally if they'd like to, but this is a single master. And the kind of advantage to this is really New York is really just like a disaster recovery location, right? So if the San Jose data center actually goes down, we can just fail over everything to New York. So the reason why you might want to do this is because the architecture is a little simpler. It's a little easier to manage. You don't have to do the whole primary key thing that I just showed you. But it's actually pretty effective because if this San Jose goes down, we fail over to New York City. And then when San Jose comes back up, it's put back into the cluster as a slave of New York. So with that, this button is, I wonder how many slides I've actually skipped. Every time I press it, it goes like 2 or 3. So any questions, obviously, feel free to contact us. Feel free to chat with me. We have MC Brown, too, sitting in here, who's definitely a replicator expert, as well as a database expert. And I'm going to turn it over to Matthew Churcher from New Voice Media, and he'll talk about how New Voice Media uses our replication or clustering solutions as well.